Hi everyone, I hope that you're all doing well. In this lecture, I want to introduce you to the theory of the chi-square test. We're going to start with the basic statistics associated with it. Then we'll walk through a chi-square test of independence, which is our two-group test. Then we'll go over the one-group test, the goodness of fit test, and then we'll do a little bit of a recap. It might seem a little bit strange to start with the two-group test here because we often start with the one-group version of a statistical procedure, but here we're going to do the two-group because it just is a little bit more intuitive, and then we'll do the two-group. So why would we do the chi-square test? Well, it allows us to use nominal variables as both predictor and outcome. So far, our T procedures required a quantitative outcome. We do already know how to do nominal analysis with proportion procedures, but that's kind of only half right. So whether we literally turn our nominal variable into a dummy as in stata, or we just effectively do so, which is what you do when you do a proportion test, so far we've been limited to focusing on basically binary outcomes and binary predictors with proportion tests. So the chi-square test allows us to work with nominal variables in their original form. It's basically a form of inference on a two-way table, and we know how to use those pretty well. So how is the chi-square different from our Z or T procedures? So we're not doing inference on a single mean or proportion, nor on a difference between two means or two proportions. We're testing to see if two variables are independent. So the primary use is for nominal variables with several categories known as polytomous variables, since these otherwise require some transformation or finagling. So here's a simple example. Is class status independent of home ownership status? We can make both of those into a dummy pretty easily, say whether someone is working class or not and whether they own a home or not. But what if we feel that's reductive? Then we could use the chi-square test, which is its appeal. It also avoids the hassle of doing many confidence intervals. So we could do confidence intervals on specific values of each nominal variable, and Stata automates that with the command proportion. But there's a handy alternative, which is the chi-square goodness of fit test for exploratory data analysis, which lets us do inference on the distribution of a particular variable. So that's quite helpful as well. So here's the recipe, and then I'll talk a little bit more about the theory. But as I sometimes like to do, it's maybe just easier to lay out the recipe. First, we determine the conditional distribution of x across values of y, or y across values of x, if the two were independent. This yields our expected values under the null. So basically what we do is we look at the marginal distribution for each variable, and then we say, okay, well, the marginal distribution should be the same across every level. Like let's say we've got some variable x. The marginal distribution of the other variable y should be the same across every level of x, or vice versa if the two are independent. And then all we need to do is basically just multiply those percentages associated with the marginal distribution, such as A% of people are lower class, self-identified, B% are working class, C% are middle class, D% are upper class, all self-identified, and then just multiply those through by, say, the raw numbers of people that are in basically each of the other variables, each bucket of the other variables, such as home ownership status. So that gives us our expected values under the null. I'll say more about that in a little bit. Then we calculate the statistic. So we take the difference between the expected value and the observed value for each cell, we square it, and we divide by the expected value, yielding that cell's statistic, observed minus expected squared over expected. Then we just add up all the cells, giving us this. Interestingly, we now have, if the null is true, a sum of squares of normally-ish distributed variables. The distribution of the sum of k standard normal variance is a unique non-normal one called the chi-square. The notation here is a little bit confusing, so just think about this as basically referring to the sum of a bunch of squared normal variates. There's not really much more intuition there to give for the notation. There's a little bit of the history. You could probably find it on Wikipedia, but it has to do with some kind of more complex statistics that we don't have time to talk about, interesting as they are. So this chi-square distribution is the sampling distribution of the sum of each cell's statistic under the null. So the chi-square distribution's shape is different in some ways to the normal. Like T, it changes a lot depending on the degrees of freedom, and it can't take negative values. But we can find areas under it, just like with the Z and T distributions. So let's go over the theory a little bit. The mean and the variance of a random variable with the chi-square distribution are easy to derive. So the mean, let's start with the fact that the variance of a standard normal variate z we know to be 1. It's also true that the variance is the expectation of the squared variable, this here, minus the expectation of the variable squared, this here. we know that the variance of z is 1, so 1 is equal to this minus this. But then we know that the expectation of the standard normal is 0, and squaring it doesn't do anything. So we learned that the expectation of a squared random variable z, where z is just the standard normal, is equal to 1. So the expected value, or in other words, the mean of this distribution, would be 1 added up however many times we have z, because the expectation of a sum of random variables is just the sum of their expectations, which is pretty intuitive. It's basically like saying that you can add the means of different groups together to get their total mean only under the condition that the sample sizes are the same. Well, when we're doing this expectation algebra, anytime you see these blackboard bold things, we're doing like population algebra here. And what that means is that we don't care about sample size. Sample size is not a consideration, basically. Like, we're not thinking about discrete draws from the distribution. So what that means is that sample size doesn't matter. So if your teacher ever told you never average averages, and then they maybe said, well, okay, you get to do it, the sample sizes are the same. Here, basically, the sample sizes are effectively the same. So we do get to do that. So that's the logic there. So the expectation of a chi-square distribution is equal to k, where k is the degrees of freedom. And when you have a simple situation where you're just summing up a bunch of random variables, the number of things that can vary is, of course, just the number of random variables. So it's k. Now, we'll have fewer degrees of freedom in our situation, to be explained later. The variance, so the variance of x, where x is a sum of random uncorrelated variables, is just the sum of all of their variances, as proved in past appendices. I probably should make it clear that this is only true when these are uncorrelated. I'll do that. The variance of a single squared z happens to be 2, which is a little bit complicated to show. So then what that means is that the variance of a chi-square distribution is equal to 2k. So some interesting facts. We'll make use of them later. How does all that fit into the analysis of a two-way table? Well, here's a helpful summary. You can read that at your leisure if you want. But basically, the cells of a two-way table can be considered to be basically normal-ish variables. Technically, they're called Poisson variables, or they have Poisson distributions. And what that means effectively is that they're pretty close to normal distributions. And in particular, they happen to have a mean and a variance, which are both their expected count. So their z-score form is the observed minus the expected over the root of the expected, and their squared z-score is observed minus expected squared over the expected. And that turns out to have a distribution that's basically the same as that of a squared standard normal random variable. So summing those squared z's or z-ish things produces a test statistic taken from the chi-square, which is, again, the distribution for a sum of squared normal variables with degrees of freedom nu equal to k, where k, for a two-way table of the type we use, I messed up the notation here. Let's change the notation a little bit. Sorry, I like to use k in place of c because c is difficult to write in a clear way on a board, but we'll change this up a little bit. So degrees of freedom nu are equal to k, where k just means some constant. And in this case, the way we find the constant is that we use r minus 1 times c minus 1, where r is just the number of rows and c is the number of columns. You'll see later on that that's actually quite intuitive why that should be the degrees of freedom, but I'll say more about that later. In fact, we might just go ahead and eliminate the parameter k here, since I think this is maybe more confusing than not. So let's go from there. And let's now go ahead and look at the practice of degrees of freedom. In other words, let's look at the degrees of freedom and see where they come from and what effect they have on a distribution. So to the right here, we see the chi-square distributions with various degrees of freedom. You can see you've got the distribution with 1 degree of freedom here, and this kind of looks a lot like just a squared normal random variable here. It seems like we've taken this other half here, folded it over, and then kind of like doubled the heights, right? Because we're going to have a bunch of duplicates. But then interestingly, as we increase the number of degrees of freedom, you can see the mean is shifting over pretty perceptibly here. And also the variance is clearly there's a little bit more spread as well. And that's kind of all fairly intuitive, I think. So again, theory aside, the degrees of freedom are just rows minus 1 times columns minus 1. A little bit repetitive, I suppose, but it's important to just know how to calculate them as well and where they come from. But again, these are kind of idealized pictures that don't necessarily have anything to do with a two-way table. There are other things that can be chi-square distributed, actually, and so the way that we get these degrees of freedom is true in this specific case, but you should think about this just generally as like the number of pieces of information that are free to vary. So these are what various chi-square distributions look like. Pretty cool. So let's talk a little bit about how that theory applies here. So if two variables are independent, then the conditional distribution of one variable should be roughly the same for all levels of the other. So here you can think about that as like the overall distribution of class status, which is 9% lower, 44% working, 44% middle, about 3.5% upper class. That means that that distribution should be the same for all race groups if the two variables are independent. So in any particular sample, you have over here in these columns, you have in this column, you have a fixed number of people in each race group. So 1,501 whites, 380 black people, 348 Hispanic people, 104 people who unfortunately had to be consigned to the bucket of other. You might notice, by the way, that this is my recode of the GSS race variables that I did for a project. So the GSS race variable itself is just white, black, and Hispanic, which is pretty unfortunate, but that is how it is. So then what's our kind of next step here? Well, pushing ahead a little bit, we're going to think about calculating the number of people that should be in each of these cells if it is true that this marginal distribution of class is the same across all levels of the variable race, here called race nu, which would mean, that all the conditional distributions are the same. And the idea here, though, is that because it has to sum to 1501, we don't actually have all four things that can vary here. Like, this is a constraint that's part of the data. So whatever three of these guys are, and here I just circled this three here, this guy has to mop up. And it's not really this guy in the sense that it's not upper class. What I've drawn here is somewhat artificial in that it suggests that one cell in particular mops up. That's really not what's happening here because no particular cell mops up. The way to think about it is just which of these are actually random variables or which of these are truly free to vary in the solution of a problem. And again, you can think about it going the opposite way too. So like this column is fixed, so only these three are free to vary. Basically, again, although it's somewhat artificial to think about any specific subset as being free to vary or not, it may be helpful to think about the submatrix here, which is you can see rows -1 here times columns -1 here. So 4 by 4, that actually comes down to 3 by 3, and we have this submatrix 3 by 3 with 9 entries. So we have 9 degrees of freedom here. That is free to vary effectively. So that's where degrees of freedom come from. Again, it's somewhat artificial in that it's not as though upper class or other are the actual, statuses of each or outcomes of each variable that are like mopping up truly. It just has to be one of them, but it's like wrong to associate it with any particular outcome. But at the same time, that might be a helpful way to think about it. So let's move on to a chi-square test of independence. The main use of the chi-square test is to test the independence of a row variable and a column variable in a two-way table as previously established. Here's a motivating example. Is race in the US a partial determinant of class status? In other words, does described race sort of sort people into different class buckets? It's plausible. So class is a relationship that's really only formally solidified once someone reaches working age. Your family's class status obviously strongly predicts your later class status, but it's not the same as it. But ascribed race is usually solidified at birth, even though that's not always true, which is itself a pretty fascinating fact, but it typically is. So race seems to precede class just temporally. So let's start with a familiar two-way table, such as the one I've already shown a few times in this lecture. We have rough evidence here for a systematic difference in class status by race. You want to note the conditional probabilities on the rows here. So for instance, among whites, their probability of being lower class in this sample was 8.19. For black respondents, 12.63. For Hispanic respondents, 9.77. And for other respondents, 5.77. So these are all, somewhat different. Working class, wow, this is really quite different. So Whites had about a 39% chance of self-identifying that way. Hispanic respondents had about a 60% chance of self-identifying that way. And then we can kind of, take a look. Whites had about a 49% chance of identifying as middle class. Black respondents only about 36, Hispanic respondents only about 28, but other respondents, although this is a small subsample, about 53%. And you can see the same for upper class. So I won't belabor the point too much, but you can just note a couple of things there. Like I said, it looks like we have some evidence here, but let's try to formalize that, right? Because it's still not huge differences, and it's really pretty hard intuitively to say here, especially with this other group, like what do we do with this other group? Or what do we do with the fact that there's lots of Hispanic respondents, but only 7 and only 12 for Black and Hispanic respondents in this upper class bucket? And, small numbers here, like well less than 100. So let's think about how we can be a little more systematic. So first we need to find the expected counts under the null. So what are these expected counts? I want you to think about a simpler example. So consider 2 almost certainly independent random variables, someone's birth month and which of 4 animals they prefer: dogs, cats, birds, and snakes. Suppose you have 100 people in a room and you know the overall distribution of birthdays and preferences for animals. Then how could you possibly predict how many people born in April prefer dogs? So if we have no reason to suspect otherwise, shouldn't it be the share a dog prefers times people born in April? So you'd find out 25% of people prefer dogs most, and about 10 people here were born in April. So we should expect to see then, about a quarter of 10 or 2.5 people, which is, not possible, but that would be what our expectation would be. Or you could go the other way and you could say, okay, well, the share of April births was about 10%, and the number of dog prefers was about 25, since we said it was 25% of 100. So then we can just go the opposite way with it. Obviously, in the first case, you're just shifting the decimal over a little bit, or in other words, you're kind of shifting the denominator around here. But otherwise, you're fundamentally just multiplying the same 2 numbers. And what you could think about doing really is you're really just multiplying the raw number of each and then dividing out by the sample size. So hopefully that's pretty intuitive. So what a chi-square test does is basically it takes that kind of naive assumption of independence embodied in the expected counts, and then it tests this. So let's see how that would apply in our specific example, which might seem a little more complicated. Note that the kind of official formula is this: it's row total times column total over table total. There's a couple of rearrangements of that I just mentioned that make more sense than what our book shows, though. So the first is row total times column total over table total. What that means is we first find the share that a given column is of the total population. That's what this does here. Then we multiply that by a given row's absolute size, which gives us how many people of that row should be in the cell defined by that row and column if the variables had no systematic relationship. Or we could go the other way about it. We could find out what share of the population a given row is, and then multiply it by a column to find what number of people we'd see in a cell defined by that row or column, or row and column, pardon me, if the 2 variables were unrelated. That's pretty abstract, but I think it'll make more sense when you see it in practice. So let's think about finding expected counts here using the column total over table total method. So here, the number of working class respondents total is 120 divided by 2,333, which is about 43%, or 43.7%. And that's what this prints right here. So what that means then is that we can say, okay, well, that gives us an intuition for how many people should be for each race group working class, because if the marginal distribution is the same for all of these groups, then all we have to do is say find the number of whites, 1501, and then multiply that by 0.4372, and we should get the number of whites who are working class. And so here, that's exactly how we do it. We could go the other way too. Oh, sorry about the animation there. And we could do it with column total, right? As the kind of thing that's the raw number, and row total as the thing that we're normalizing by. So here, what if we say found the total number of Hispanic people as a share of the population, to be more exact. So here that's 348 divided by 2,333, and we get 0.149. So Hispanic respondents were about 15% roughly of the population, assuming that we, I probably should put sample there. I mean, that's making the jump from sample to population. Here we're not really questioning that directly, we're questioning something a little more specific. So then what we could do, for instance, to say find the number of Hispanic people who are, say, lower class, we would just need to multiply this number here, 15%, by the number of lower class people, and that should produce this number here. So that gives you a sense for, kind of basically how this works. You find out what share a given group, either race or class, is, and then you multiply it by the raw number of people in the opposite. So you find out what share a race group is, then you multiply it by the number of people in a class status, or you find out what share a class status is, then you multiply it by the number of people in a race group, and that gives you the number of people you should expect to see in that cell. So let's look at an example, but what we want to do is also turn this into the actual chi-square statistic formula. So the chi-square statistic that we're hoping to get is this. It's sigma, which means to sum over a bunch of variables or a bunch of anything that's got kind of an index. Here I don't explicitly put the index in. When you don't have an explicit index, which is bad notation, but it's kind of hard to do in Google Slides, what that's telling you to do is just sum over whatever the obvious thing to sum over is. Here that would mean cells. So in each cell, we're going to calculate the observed minus the expected, square it, then divide by the expected count before summing across cells. But let's go ahead and actually do that for a given group. So find the observed minus the expected squared for over expected for self-identified lower class whites. So we would first find the expected count. So we could do this in one of two ways. Here I chose to find the total number of lower class people, which is going to be 211 divided by 2,333, and then multiply it by the number of whites, that's 1501. And so here we do that just right here, and we get 135.8. Then we take observed, which is 123, minus expected, which is that number here, square it, and then divide by 135.8. That gives us 1.204, pardon me. And that's our chi-square statistic for that cell. This is nice, but it'd be tedious to do it for all 16 cells. So Stata will actually do that for us. This code here, tab var1, var2, expected, gives the expected frequencies where the row conditional probabilities or column conditional probabilities were previously given. What it does, and you should do this even though you don't have to, strictly speaking, to run the chi-square test, it allows us to check that we adhere to the guideline that no more than 20% of expected counts are less than 5. So if we look at our expected counts, only 1 is here, less than 5. So we're good there because this is 1 out of 16 cells. 1 in 16 is less than 0.2. And that no expected count is less than 1, which is also true. These are known as the Cochrane rules, by the way, and they're kind of arbitrary, but you just have to deal with that. Then we can grab the expected counts from the table, and we could calculate a chi-square statistic by hand if we wanted, but I don't think we should do all the summing by hand. But what this lets us do is at least inspect the expected counts. Then what we can do is have Stata just run the test for us. So we can write tab var1, var2, the order doesn't matter, and then write chi2 here. And what that does is it calculates the relevant statistic for each cell, observed minus expected squared over expected, and then it sums across the cells to give the test statistic. It also calculates the degrees of freedom for us here. As previously mentioned, that is in this case 9 because we have one column that's not free to vary and one row that's not free to vary. So again, slightly playing fast and loose with the rules here. You can think about the matrix that's actually free to vary as the submatrix here. Our actual chi-square statistic is this thing here, 83.43. That doesn't have a really intuitive meaning apart from we're this far out on a sampling distribution, so we have results this extreme or more. But it's not quite the same thing. Like, it's not, in previous situations, for instance, we've seen that a t-statistic is fundamentally a normalized mean or a difference in means. Here, it's harder to say what it is apart from just it's the normalized, basically, sum of a bunch of squared random variables. That's about it. I should say standardized, not normalized, by the way. So we get our p-value here, and this is easier to interpret. What this tells us is that this is the probability of data such as these given the null hypothesis. It's extremely unlikely or improbable to be most exact. So we reject the null of independence here. This is what this looks like on the sampling distribution. Here in red, as I often do, I marked the most common alpha, 0.05, which you'll see later on corresponds to a test statistic of 16 and change for degrees of freedom 9. And then here's our actual test statistic over here. Obviously, it's extremely small, so we reject the null here because our AUC, our p-value, is much smaller than that for the cutoff. And really here, the choice of a cutoff doesn't matter because we have a p-value that effectively rounds to 0. So note a couple interesting things that I mentioned earlier. This chi-square distribution is only defined for positive values because our test statistic is always positive. We can't get a negative sum from a sum of squares. And that's like, for instance, the reason that we square when we take the variance, as we've learned before. So for our class, our tests and p-values are therefore always one-tailed, just something worth noting. So how do we interpret these results? And I noted this already, but it probably deserves its own slide. Some stuff is different here, like the shape of the sampling distribution and the statistic, but we're basically doing the same thing that we always do with hypothesis tests. We figure out the sampling distribution of our statistic under the null. We saw that before. It's a chi-square distribution with the relevant degrees of freedom. Then we calculate the test statistic. Then we ask, if the null were true, how often will we get results this weird or weirder purely by chance? The relevant table also can be shown here. It's not as important because it's harder to work purely by hand for a chi-square test, but I'll show that in a minute too. So here's that table. Note that it works exactly like table C. So we find the degrees of freedom, that's 9 here. Then we find alpha in the table, it's one of the p-values here, 0.05. We find the cell with a critical value, that's 16.92 as I mentioned before. We see if our test statistic exceeds that critical value. It does by a long shot. It's not even in the table. So we conclude that we reject the null here of independence. So what does that actually mean practically? What it means is that the two variables are related. But our test is pretty coarse, so it can only tell us that we reject the null that the two variables are unrelated. That's a lot less detail than, say, a difference in means. So for detail, we look at the contribution of each cell to the total test statistic. So for instance, these are all chi-square contributions. You can see that we already calculated it for whites. That was this here, but we didn't look at it for other groups. We let Stata do that for us. And it looks like Hispanic working class individuals by far play the single biggest role, as well as Hispanic middle class individuals, and then white middle class and white working class, sorry, I did that in reverse order, kind of coming up third and fourth there, and then black lower class, black middle class. Those are all the ones that I think are like notable here. Notably, this on its own would be enough to reject the null, and then these two summed would be enough to reject the null. So that's one way to kind of use your offhand intuition. Note that each cell's contribution is necessarily positive because it's squared. So to figure out the direction and the deviation from each cell, we need to go back to the expected count. So now that we've identified the cells that matter most, it's this one, this one, this one, this one, and this one. You can just write those down in your kind of research log, or you can, as I'll show later on, you can print them both in the same table. I just didn't want it to be too messy. We can actually show that here. I'll do that in Stata. So let's change our working directory here. And I'll just show that briefly. Let's pick something simple. Let's pick, we'll do the example from the project. I think that's a good one. Yeah, dwell on. So this is our two-way table for class and whether someone owns or rents their home. But if we did want to put in that chi-square statistic, we could put all this in here. And then you'll see that this is a quick way to do it. So you can put the frequency, the expected frequency, and the chi-square contribution. So for instance, in this particular table, we can see like each cell's contribution. So the total was 104. So some of the bigger ones are like middle class and renting or owning, working class, owning or renting. I mean, pretty much all of them are significant. Upper class, not as much. So then what we see here is, okay, we've got these differences here. So for instance, if you think about owning a home, more middle class people owned a home than you would expect. An easy way to tell the expected from the observed is that the expected will very often be decimals or have decimals past the ones place. And so then you can gauge the size of the contribution here. So you can put it all in one table if you want. I just thought that might be confusing here. So what do we conclude overall? We reject the null of independence between the race and the class variables. These two things probably have a relationship in the population. Basically, under the null of no relationship, we saw results that would be extremely weird if the two were unrelated. In particular, whites have more members of the middle class and fewer members of the working class than one would expect if they were unrelated. The opposite is true for Hispanic respondents. Overall, our results are very different to what we would expect under the null. By the way, note that you can combine code from before that I did step-by-step for pedagogical purposes. So for example, in a do file, you could run the following code like this, which prints basically everything that you need to analyze this question in one table, although you need to look carefully at the key. And I showed that before. By the way, the race variable, as I mentioned before, that I'm using in this set of lecture slides is based on code that I wrote for a project of mine long ago. So this is going to print a different race variable, and the results will differ slightly, but the analysis would be basically the same. So let's look at a goodness of fit test. We're now transitioning to thinking about just one variable, which again is the opposite order that we've normally gone in constructing, our kind of tests, right? We usually start with the one group version, and then we look at differences between them. But here it's a little bit easier to explain once we've done the two group. So what would be a goodness of fit test? What does it really do? Well, a lot of times before we conduct an analysis, we want a rough sense of what the population distribution is like for each variable. You could do confidence intervals for proportions of the individual possible values of each variable, but you can also just do direct inference on the distribution, which we otherwise haven't done. So for instance, if we were to do inference on a variable and see if it were normal or not, we would use what's called the Kolmogorov-Smirnov test. That test is really interesting, but it's one that we haven't learned how to do. So far we haven't actually done inference on entire distributions. It's a little complicated with quantitative variables. With qualitative variables, it's actually relatively straightforward. Doing the chi-square goodness of fit test is one way to do that. So we basically adapt the test of independence to a one variable setting. We're going to find out if the values of our variable are consistent with a particular population distribution. So for example, on the next page, we'll test the null hypothesis that the ratio of union membership to non-membership in the US is 88 to 12, which is a value that was current several years back, but may or may not be consistent with the observed data today. Here's my practical advice. On the project, use a judgment call if you want to do a chi-square goodness of fit test for the univariate analysis. Some things you might consider would be, how many possible values of the variable are there? Is my goodness of fit null a reasonable hypothesis, or is it random guesses? The alternative that you could use is a set of confidence intervals using the command proportion, and you may want to consider that instead. I've already shown how to do that in previous lectures, so just give that some thought. So let's go ahead and carry out our example. We're going to test the claim that union members form 12% of all US resident workers, and the way that we're going to get our expected counts is now, instead of using the marginal distribution of a second variable and then saying, okay, that marginal distribution should match the conditional distribution for each value of the first variable, and then we'll find the counts on that basis. Here, we just only have one variable, so we're going to use our basically expected percentages, or our percentages under the null, to directly calculate the expected counts. This part's pretty easy, actually. So for instance, we're going to find out what basically 12% is as a decimal. It's 0.12. And then we're just going to multiply that by the total number of people in the sample, and get whatever 12% would be. That's our expected count. So for here, that happens to be this number here, 18,567.24, and then we'll do the same for non-union workers. So multiply 0.88 times the total, and we get these two numbers here, which together sum to this here. Again, note that it's not a problem for the expected count to be a non-integer. It just means what we think would happen. This is very much like when we did the binomial distribution and we had expected counts that were non-integers, even though the binomial is a count variable. It just turns out to be kind of complicated like that, but that's okay. It's not a big deal. So then we calculate our chi-square statistic. For union workers, we take the observed amount, 17,716, minus the expected count. I won't read out that long number again. It's the thing we just found. We square it. We divide by this here, the same count, which for a Poisson variable is its variance. So we basically end up with what's a squared z-score. And we get the chi-square statistic here, which is 39.03. And then for non-union workers, we get 5.32. Taken together, our statistic is 44.35. And we can do the same thing in stata here. You'll need to install this command here. You can write find it and then chi-square goodness of fit test. I'll actually start a fresh stata session and show you how that works here. So we'll start stata fresh. And you can write here find it, CSGOF, like this. And you'll note this is not actually a command that you can install with the usual syntax of SSC install CSGOF. I'm sure there's probably a good reason for why some authors don't do that. It's pretty annoying, but that's okay. So then what you need to do is just click on this and then click here to install. and then you'll see it's already been installed in my case. You can also find, like here, I, for instance, was looking up how to do this, and you can find guides to installation on the internet. But yeah, for the most part, commands can be installed with ssc space install space the name of the command, but this is an exception. Okay, so we do that in Stata, and then the syntax is pretty straightforward. We just write csgof, the name of the variable, comma, and then expected percent or exp perc like this. And then you just write the, basically you do need to write the numbers in order, and you write them as like numbers larger than decimals, or you basically write them as percentages, which is also kind of annoying because that's counter to the normal Stata syntax, but this is how you would do that here. In this test, the claim that the percentage is 88 for non-union workers, 12 for union workers, and you see that they get the chi-square statistic that's the same as ours, and the associated p-value is effectively 0. So there's basically no chance of this happening just by coincidence under the null, which might seem kind of surprising because we have a sample that's pretty darn close. Non-union workers were 88.55, union workers were 11.45, but note that we have giant sample sizes here. And so what that means basically is then these counts kind of reflect that giant sample size. So the deviation really is, even though it's not that sizable in a certain sense, it's still kind of sizable, in absolute terms. So it ends up being significant. Note also, this is just kind of an odd and an end, that chi-square tests work for simple 2x2 two-way tables. And recall that two-way tables generally, even though we study them often in their kind of canonical form, which is a table that's not only two-way but 2x2, the two-way simply means that there's basically two variables involved. So there's plenty of two-way tables, such as the one we worked with for the majority of this lecture, which are, two-way tables, but they might be like 4x4 matrices. Here we actually have 2x2 two-way tables. And the reason I'm pointing this out is that we could just do a proportion test anytime we have a 2x2 two-way table. So we basically just end up with an alternate means of conducting a test for the difference in proportions. And you'll note that the chi-square statistic is actually just going to be the square of our z-score, somewhat remarkably. No proof offered, but take a higher level class if you're interested in that. Basically, this just amounts to doing the same thing. Proportion test gives you more information, though, so you may want to do that if you can turn what you're doing into a proportion test. Here I just picked an example from the CPS. I tested whether or not people were more likely to be men or women based on whether they were citizens or not. It turns out that the gender distribution conditional on someone being a citizen or not doesn't differ. So we read this test in the same way. We get this z statistic here. It's basically negative 1.45. That happens to be, when you square it, the chi-square statistic here. And note that we actually get the same p-value here pretty remarkably, which is a cool fact. So these work in either situation. You could use a chi-square test with these data, but it's better to do the proportion test since it's more informative. Note here that we would have to go back and do our analysis in the way that we've been doing it in order to, like the way we've done it in this lecture, go back and look at the expected counts and look at the differences from them and look at the chi-square contribution. And here with the proportion test, we can get a little more information and just see, it's pretty straightforward. It's almost like hard to say too much, but basically the difference between the two groups here, we had this observed difference in proportions that was about half a percentage point, and then relative to the standard error under the null hypothesis, that ratio was 1.45 in absolute value terms, and that's just not that big of a z-score, end of story. Whereas here we have to do a little bit more analysis, and it's a little bit less clear too. Like this is very elegant. We would just say the raw difference appears fairly small relative to the standard error. It's small as a standard deviation basically, or as a z-score. And then here we have to like go through and again kind of compare the expected counts, and it's not as clean. But sometimes chi-square tests are the best that we can do. So I wanted to summarize some fine points that I showed along the way as a way of wrapping up, since there are a lot of kind of little bits and pieces of detail here. So first of all, this is a way to find the expected count. This is what they are computationally. Remember the two arrangements that I showed, the two rearrangements. Using table D, it works like table C. You pick your degrees of freedom given by the sample, so you don't really pick it, you find it. You find your p-value cutoff, you do pick that, and then you find the critical value, which is the intersection of the df row and the p-value column.
If your observed statistic is larger, your results are significant at that level. Simple as. In practice, you can just use software for the most part. Minimum expected counts, there's 2 rules. No cells can have less than 1 expected individual, and less than 20% of the cells, or really there should be fewer, have fewer than 5 expected individuals. Sorry for my atrocious grammar. And finally, you should always examine the contribution of each cell for more detail. We will take off points on the data analysis project if you don't do this. So the chi-square test is not a get out of jail free card to do uber minimalist analysis. You actually do need to do that analysis because people who are doing proportion tests and difference in means and regression are basically doing that additional analysis that chi-square tests don't perform automatically, but you do need to do them. So thanks everyone for watching. I hope you enjoyed the lecture, and I look forward to seeing you next time.